Right now, as you watch this, something is passing through you. Not air, not light. Something that has no name you'd recognize, that doesn't interact with your body in any way you can feel, that has been flowing through walls, through planets, through you, for the entire age of the universe. You can't stop it. You can't detect it. You don't even know what it is. And here's the part that should unsettle you. Neither do we. We've been looking for 90 years. Let's start with something that seems simple. How does a galaxy spin? Think about our solar system. Mercury, the closest planet to the sun, moves fast, over 100,000 miles per hour. Neptune, the furthest, barely crawls, about 12,000 miles per hour. This makes sense. The closer you are to the center of gravity, the more you feel it, the faster you move. The further you get, the weaker the pull, the slower you go. Astronomers assumed galaxies work the same way. Stars near the center, fast. Stars near the edge, slow. Basic physics. Then they actually measured it. And the stars at the edges weren't moving slowly. They were moving just as fast as the stars near the center. Sometimes faster. Thousands of galaxies, checked and rechecked. Same result every time. Now here's why this is terrifying. By our best equations, those stars shouldn't be there. They're moving fast enough to escape. The gravity from all the visible matter, every star, every cloud of gas, everything, is not enough to hold them in orbit. They should have flown off billions of years ago. But they didn't. Something is holding them, and we cannot see it. The first person to seriously propose this was a Swiss astronomer named Fritz Zwicky. The year was 1933. Zwicky was studying a cluster of galaxies, over 1,000 of them gravitationally bound together. He measured their speeds, did the math, and got an impossible answer. The galaxies were moving way too fast for the visible mass to contain them. The cluster should be flying apart right now, in real time. His conclusion: there has to be invisible mass we're not accounting for. Mass that doesn't emit light. Mass that is, in his words, Dunkelmaterie, dark matter. The scientific community's response was basically, interesting idea, Fritz. Moving on. He was ignored for 40 years. The person who finally forced the world to pay attention was a woman named Vera Rubin. And the way she did it is one of the great scientific stories of the 20th century. Rubin was an astronomer in the 1970s, at a time when women in professional astronomy were still rare. She spent years making careful measurements of how fast stars move at different distances from the center of their galaxy. It was painstaking work. Thousands of data points, galaxy after galaxy. She was expecting a textbook result. Fast near the center, slow at the edge. She was ready to confirm what everyone already believed. What she got instead was a flat line. Not slowing down, not speeding up, just flat. Constant speed, all the way out to the very edge of the galaxy and beyond, into regions where there were barely any visible stars at all. There's only one way to get that result. Each galaxy must be embedded in a massive, invisible halo of matter. Matter that extends far beyond what we can see. Matter that outweighs all the visible stars by 5 or 6 to 1. Rubin checked her data. She checked again. She checked it across dozens of galaxies. It held every time. By the 1980s, the scientific community had accepted it. Most of the matter in the universe doesn't shine. Everything we've ever seen with our eyes, every telescope, every photo of space, that's the minority. The universe is mostly something else. But here's what no one told you. We still have absolutely no idea what that something else is. Maybe you're thinking, okay, but how sure are we? One observation can be wrong. One astronomer can make a mistake. Fair. So here's what we actually have. 5 completely independent lines of evidence. 5 different methods. 5 different teams. All reaching the same conclusion. First, the rotation curves. What Rubin measured, confirmed now in thousands of galaxies across the observable universe. Second, gravitational lensing. Einstein showed that mass bends light. We can use that bending as a scale, measure how much light warps around a cluster, calculate how much mass caused it. Every time we do this, there's far more mass than we can see. Third, and this one is almost cinematic, the bullet cluster. In 2006, astronomers watched two galaxy clusters that had collided and passed through each other. The hot gas from both clusters, the normal matter, slowed down during the impact and got left behind in the middle. But the gravitational mass of each cluster kept moving straight through as if nothing had happened. The two halos of invisible matter passed through each other like ghosts. You could literally see the dark matter and the normal matter separate. Fourth, the echo of the Big Bang. The universe is filled with faint microwave radiation left over from its earliest moments. The pattern in that radiation encodes the exact ratio of dark matter to normal matter in the early universe. The ratio matches what we calculate from galaxies today, about 5:1. Fifth, if you simulate the large-scale structure of the universe, all the cosmic filaments and voids, without dark matter, you get a smooth, featureless result. Nothing like what we see. Add dark matter, and the simulation produces a universe that looks exactly like ours. 5 independent methods. One answer: something is there. So if we're so sure it exists, why haven't we found it? This is where the story takes a strange turn. For decades, the leading candidate has been a type of particle called a WIMP, a weakly interacting massive particle. The theory is clean: a heavy particle that barely interacts with normal matter, but just enough that if we built sensitive enough detectors, we might catch one colliding with an atomic nucleus. So physicists built detectors, incredibly sensitive ones, buried deep underground to block out interference, in abandoned gold mines in South Dakota, under mountains in Italy, beneath lakes in Canada. They ran them for years, watching and waiting for a single collision. Nothing. They built bigger detectors. Still nothing. They built even bigger ones. Nothing. Meanwhile, the Large Hadron Collider, the most powerful particle accelerator ever built, has been smashing protons together at energies that, according to theory, should have produced dark matter particles. It has run for years. It has found a lot of interesting things. Dark matter isn't one of them. Other candidates exist. Axions, particles so light they're almost unimaginable. Primordial black holes that formed in the universe's first second, before stars even existed, and have been drifting through galaxies ever since, invisible and quiet. Sterile neutrinos, ghostly particles even less detectable than the neutrinos we already know about. And then there's the possibility no one wants to say out loud. What if dark matter doesn't exist at all, and our equations for gravity are simply wrong at large scales? Most physicists think this is unlikely, but it can't be fully ruled out. That's how deep this problem goes. Here is where we actually stand. 90 years after Zwicky, 50 years after Rubin, billions of dollars spent, the most advanced experiments ever built. We know dark matter is there. We know where it is. We can map it. We know how much of it there is, roughly 27% of the total energy content of the universe. For comparison, everything you have ever seen, every star, planet, galaxy, atom of normal matter, makes up about 5%. We're the small print, and we cannot tell you what makes up the other 27%. Now, you could hear all of this and think, 90 years, no answer, sound like failure. But look at what we've actually accomplished. We know dark matter isn't made of protons or neutrons, the stuff that makes up you, the planet, the stars. We know it doesn't carry electric charge. We know it barely interacts with itself. Every failed experiment has closed a door. We are running out of wrong answers, which means we're getting closer to the right one. And when we find it, not if, when, it won't be a small correction. It will be new physics, something outside everything we currently know about matter. The kind of discovery that rewrites textbooks. The thing that's been holding galaxies together since before a solar system existed has been here the entire time. Invisible, patient, completely indifferent to whether or not we figure it out. But we're getting closer. If you found this interesting, the next video is about something even stranger. Dark energy, the force that isn't holding the universe together, but is actively tearing it apart. And it's accelerating. Subscribe so you don't miss it.